just going to go quickly here. If real numbers A, B, C, and D satisfy the sum of A, B, C, and D to be 20 and the sum of its squares to be 2022, the largest possible value of D can be written as P plus Q root R over S, where they're positive integers, and GCD of P, Q, and S are 1. And R is not divisible with square of any prime. And we can get the sum of these values. So we see that in order to find the largest possible value of D, we need to separate the D's from the rest of the equation. So we can do A plus B plus C plus 20 minus D, A squared plus B squared plus C squared equal 2022 minus D squared. Now we see we have a the sum of the real numbers and the sum of the squares of the real numbers. So we can probably think, and since we see we need to find the largest value of D, we need to like kind of bound it in a sense. And so we need to use some inequalities, and the one that pops up to mind here is actually using the Cauchy-Schwarz, because it very much looks like we need to use it. But we need to use a special kind of Cauchy-Schwarz, and we'll derive it quickly here. We see that Cauchy-Schwarz gives us some A1 squared plus A2 squared all the way to AN squared times B1 squared, B2 squared, all the way to BN squared is greater than or equal to A1 B1 plus A2 B2 plus all the way to AN BN squared. But we want it so that we have this to be just a regular B1, B2 all the way to Bn, but then to offset that, we need something A1 squared over B1 plus A2 squared over B2, and so on and so forth. So we make a substitution. We do AN maps to AN over root Bn, and then Bn maps to root Bn for all n. And so we have A1 squared over B1 plus A2 squared over B2 plus all the way to AN squared over Bn times B1 plus B2 all the way to Bn is greater than or equal to, if we multiply everything together, it's where we get A1 plus A2 all the way to plus AN squared. And if we divide, we get A1 over A1 squared over B1, A2 squared over B2, all the way to AN squared over Bn is greater than or equal to A1 plus A2 plus AN squared over B1 plus B2 plus Bn. This is actually known as T2's lemma. It is basically a special form of the Cauchy-Schwarz inequality from this substitution here. Right. So we're actually going to use this with these two equations. We see that A squared over 1 plus B squared over 1 plus C squared over 1. We let the tops be the squares and the bottoms be just 1. Since we know A squared plus B squared plus C squared, we know that this is going to be greater than or equal to A plus B plus C squared over 1 plus 1 plus 1. That's A squared, A plus B plus C quantity squared over 3. So now we have actually bounded what we wanted here, because recall from these two equations, we could just substitute and solve for D. So just multiplying each side, you get 6,066 minus 3D squared is greater than or equal to 400 minus 40D plus D squared. Moving everything to each side, we get 4D squared minus 40D minus 5666 less than 0. Dividing by 4, we get D squared minus 10D minus 1416.5. And using the quadratic equation, we get D less than or equal to, or we'll solve for D here. We get 10 plus or minus 100 minus 4 by 1 by 1416.5 over 2. We simplify this, 1416.5 times 4. 0.5 times 4 is 2, so we'll add 2. 1416 by 4 is 5664. Is 5666 plus 100. I found negative here. You get 5766 over 2. If we factorize 5766, we get 2883. 3, 3, 961, but 961 is 31 squared. And so this factors it to 10 plus or minus 31 root 6 over 2. And from here, you can manipulate these inequalities you want, but we're technically done because we know that one of them will be larger, one of them will be smaller, and then the x's will be in between. So we get 10 plus 2 plus 31 plus 6, and that's going to be 37 plus 2, 39 is 49. And we go back. That's answer choice E, since we actually don't have 49 in the answer choice now. We're done.
This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.